and the corresponding integrated rate law. So what we're going to learn today is first we will learn the principle of chemical kinetics, which is the chemical reaction rate. So actually the length scale that we are dealing with today is more like a macroscopic, which is relatively large or the real world scale rather than the atomic scale. So until the last week we have learned the motion of molecules and like a gas or liquid phase, and we have dealt with all the motion of molecules in the atomic scale and the relatively large scale, which is the real world scale. So for today, we will learn the how can we determine the reaction rate, and we're gonna deal with this reaction rate in a macroscopic scale. So for that, firstly, I will introduce you some experimental technique for measuring the rate of chemical reaction and rate of chemical reaction in gas phase or in liquid phase. And then I will introduce the definition of rate law, which can account for the rate of chemical reaction. And then you will learn the how can we determine this rate law in the experiment, and eventually we want to see how this reaction rate is going on during over some time scale and some time evolution. So we're gonna learn the time evolution of molar concentration of reactant and the product, which defines the rate of chemical reaction by simply integrating the rate law derived from these parts. So now let's consider the hypothetical chemical reaction where the reactant A and B react together and form a product C. So we want to know after some amount of time after the reaction started, tracing the amount of this reactant and the product will give us information about the time evolution of this concentration of reactant and the product, where we can get some information about the reaction speed. So here the bracket A, B, C is the molar concentration. So measuring the amount of this reactant or product during the chemical reaction in time will give us information of the rate of reaction, which is the speed of this chemical reaction. Then let's discuss how we can measure this amount in the chemical reaction in experiment. So one method of measuring the concentration of reactant and product is measuring the pressure of the system, the system where the chemical reaction is occurring. So this method is useful for if the phase of the reactant and the product are both a gas. So let's take an example of this N2O5 gas. The reaction that this N2O5 gas decomposing into the nitrogen dioxide NO2 and the O2 oxygen gas molecules. So let's consider initially we have N mole of N2O5 gas. And then since it's before the reaction, we have the 0 mole of nitrogen dioxide and the oxygen gas. So let's say after some time t, the amount, let's assume that the fraction of N2O5 gas that has been that has reacted as the alpha. Then in total we have the N multiplied by alpha mole of N2O5 gas has been reacted, and then we have this product of the nitrogen dioxide with the 2 N alpha mole. So the reason for we are having 2 is the decomposition of 1 mole of N2O5 will produce the 2 mole of nitrogen dioxide. And then similarly, since one N2O5 will produce the half mole of gas molecule, the oxygen gas molecule, so we will have a half an alpha mole of oxygen gas. So these are the amount of the reacted. So this is the amount of reaction. So actually the remaining the nitrogen dioxide and the gas molecule are same with the reacted ones. However, for this N2O5, so since this is the amount of reaction, so the remaining mole of this N2O5 is N1 minus alpha. Yes, so we are subtracting this N multiplied alpha from this N. So we have this amount of gas molecules after N alpha mole of N2O5 is reacted. Then the total amount of gas in the initial state is the N mole. However, after the reaction, so adding those three values, then we will have N 1 plus 3 over 2 alpha. So since this alpha is somewhere is between the 0 and 1, we know that this value is always larger than this initial N. So then let's calculate the pressure of the system using the given information. So using the ideal gas law, we can estimate the pressure of initial state is which is a P0 is N RT over V. So if we assume that the V and the T is constant, then we can also calculate the pressure of this the state after the reaction. And the pressure is N 1 plus 3 over 2 alpha multiplied by RT over V. And we know that this, there's a typo. So this N should goes away. So this N RT over V is a P0. So the pressure of pressure after the reaction is 1 plus 3 over 2 alpha P0, which is higher than the initial state. So if we know like what kind of reaction is happening, and they're in a gas phase, then if we know this, then we can measure the pressure of the system. Then from these equations we can calculate this alpha value. That we can estimate how much this N2O5 reactant has been reacted and produced this product. So this is one way of monitoring the chemical reaction if the reactant and the product are in gas phase. So next method is using the spectrophotometry. So this method is useful when one of the substances in the reaction mixture has a strong the characteristic of absorbing the light. So for example, let's say we are reacting the hydrogen gas and the bromine gas and forming the HBr. So, but this the bromine gas absorbs the visible light very well. So by measuring the intensity of the visible light that has been absorbed by this reaction system, so let's say at the initial stage, since we have a lot of the bromine gas, the visible like a large portion of visible light will be absorbed by the gas molecule. But as the reaction goes on, the concentration of the bromine gas will decrease. Then the amount of visible light that are being absorbed by this substance will be decreased. So by measuring the intensity of the light that's trespassing this chemical reaction, that we can estimate the concentration of this bromine gas during the reaction. So by measuring that intensity, then we can trace the concentration of the bromine gas. Ultimately, we can trace trace the molar concentration of all the reactant and the products. The another method is measuring the tracing the conductivity of the system. So this one is this method is useful when the reaction changes the number of type of ion in the solution. So we all know that the ion is a charged molecule, so it contributes to the conductivity of the solution. So in this case, this conductivity method is useful for the liquid phase, liquid solution phase, which containing the some molecules that can be ionized. So since the number or the type of this ion will be changed upon the chemical reaction, it will change the overall conductivity of the solution. So for example, so this molecule, if this molecules react with the with water, then it will produce this chlorine ion and the hydrogen ion. So since those two are charged, while the water molecule or this molecule is not a charged molecule, which is ion. So after they are those two are reacted, the overall conductivity of the solution will be increased because we have the charged particles. So another way is measuring the pH. So for example, in this reaction, so we have some hydrogen ions in the product, so it will change the pH of the system as well. So by measuring the conductivity or the pH of this solution, we can estimate the concentration of this hydrogen with respect to time and get an information of the reaction speed. So there is also many other methods of such as the mass spectroscopy, which is the gravimetric, the chromatography, and the NMR. So there are the few like some ways to measure this molar concentration of a chemical reaction during the over the time. So the important thing from here is we need to select the right measuring method for your chemical reaction system. So now let's discuss how we can define a rate of reaction from the information we have obtained from the experiment by measuring the pressure or the conductivity or the pH, which will give us information of the time evolution of molar concentration of reactant or the product. So let's consider some general chemical reaction that A and the A plus 2B will produce the 3 mole of C and the 4 mole of D. Then with some experimental method we have discussed in the previous slide, we are able to measure the molar concentration of reactant and the product. In this case, the reactant will be A or B, and the product is C or D. So we measure the molar concentration of them as a function of time. Then we will have such graph. So this is the concentration of reactant with respect to time, and this is the concentration of product with respect to time. So it's quite straightforward that this reactant will keep decreasing because as the reaction goes on, the amount of reactant will decrease, and that reactant will make a product, so the concentration of product will keep increasing with respect to time. So basically, we want to know the rate of reaction, which is the speed of this reaction. So by taking the derivative of this slope, which is a derivative of this curve, which is a slope at a time t of each curve, is the rate of reaction. So basically, if we know the speed of like how fast the reactant A or B is decreasing, that can define the speed of this overall chemical reaction, because the rate of decreasing this reactant is the same as the rate of increase in this the product. So the slope of this product and the reactant will give us information of this chemical reaction, and those slopes should be the same. So basically, when time is greater than 0, which is after the reaction started, the rate can be defined as the slope of this molar concentration, slope of the curve that describe the molar concentration over time. So basically, the unit of this slope is the d molar concentration over dt. So then now let's see the like a rate of consumption of the reactant, which corresponds to this curve. Then the slope of, yes, for example, then the slope of the decreasing in the molar concentration of A is minus dA over dt. And it should, since we are consuming the like 2 mole of B per 1 mole, we have negative 1 over 2 here for the slope of the slope in the molar concentration curve for a substance B. So then, yeah, those two should be are the same, but somehow this 1 over 2 is tricky to understand, but I will show you some easy way to understand it. So so the rate of consumption is just simply the curve of this the molar concentration of reactant with respect to time, but there are some factor which is the stoichiometric coefficient of the reactant. So one thing you have to know that we have this negative sign for the reactant, because this reactant is keep decreasing over time. So we always have the negative slope. So in order to make it a positive value, we will have this negative sign for the rate of consumption of reactant. So similarly, the rate of formation of product, so there's typo, is not product, is product. And the rate of formation of this product is the slope of this curve, which is the molar concentration of product with respect to time. And so now we don't have the negative sign because it's always positive over time, since we are keep making the product as this reactant decrease. So we don't have the negative sign for the products. And yes, so similarly to this rate of consumption, we have this the constant factor 1 over 3 and the 1 over 4, which is 1 over the stoichiometric coefficient of this C, and the 1 over 4, the stoichiometric coefficient of this D. So yes, since the slope of this like dC over dt and the dd over dt is always positive, we also have the positive value for the rate of formation. So if you summarize summarize these two relations, we get this relationship that the rate of consumption of reactant is the same as the rate of formation of product. So actually, those two values are we define those two values as the rate of rate of chemical reaction. And just keep in mind that we have the negative sign if is the slope of reactant, and we always have the this 1 over stoichiometric coefficient factor in front of it. So then why we have this 1 over stoichiometric factor here? So let's consider some hypothetical reaction between the hydrogen and the oxygen molecule. So if we have let's say we have 2 mole of hydrogen gas molecule react with the 1 mole of oxygen molecule, they will form a 2 mole of the water molecule, which will be like this. So let's say this reaction occurs over 2 seconds. Of course, it's not. Maybe this will happen much faster than the 2 seconds, but as I said, this is a hypothetical situation. So in this the configurations, we have 2 mole of O2, which is this our red circle, and we have 4 mole of this hydrogen. Then after the reaction, let's say we have formed the like 2 mole of water molecules. So we have 2 water molecule, and the left, and there is 1 mole of oxygen that is not reacted, and the 2 mole of hydrogen that is not reacted. So that simply so let's say, so if we don't consider this the coefficient value, sorry the stoichiometric coefficient, then the rate of the rate of consumption of this the oxygen molecule is so since there is a decrease in oxygen molecule from 2 to 1 mole, so we have a 1 mole change, and it occurred for a 2 seconds. So now we have the 0.5 mole per second of speed. So now let's see the hydrogen atom. They can see that it decreased from 4 mole to the 2 mole for 2 seconds. So now we have a 1 mole per second of speed of consumption. Sorry, the rate of consumption of the hydrogen molecule. Then now let's see the rate of formation of this water molecule. So initially we have 0 water molecule, but now we have two water molecules. So the change in concentration is 2 mole, and it occurs for 2 seconds. So we have a 1 mole. So we have a 1 mole per second of rate of formation. So we can see that for the rate of hydrogen consumption and the rate of the water production has the same rate, but the rate of the consumption of this oxygen molecule is the half of the other two. So this is because the stoichiometric coefficient is not considered here. So let's say so if we consider this stoichiometric coefficient, then we have 1 over the nu O2. So we'll have the which is the stoichiometric coefficient of oxygen. So it's 1 over 1. Then it's the same. It's the same. The 0.5 mole. However, for hydrogen, we have the coefficient, the stoichiometry of 2. Then we'll have a 1 over 2 factor here. So we have a 0.5 mole per second. Similarly, for the water molecule, the stoichiometry is 2 in this the reaction. So we have a 1 over 2. So we have a 0.5 mole per second. So actually, there is a more rigorous way to deriving this equation. Why we are having this the factor of the stoichiometric coefficient, but I think this is more straightforward. So one thing you have to remember is even the rate of reaction is highly related to the change in molar concentration of product or reactant over time, but you have to consider the relative amount of reactant of product with respect to the other reactant or other product. So now you stop your video and try to solve this example. The rate of formation of NO, which is the molar concentration of NO dt in the reaction of this. So these are the gas phase reaction forming the 2 mole of NO and 1 mole of bromium from the 2 mole of NOBr, and is reported as the 0.60 millimole diameter minus cube per second. So actually this means that the rate of formation of this compound is like this. So then what is the rate of formation of Br2 and the NO and the rate of consumption, the NOBr, which is a reactants. So I highly recommend just stop the video for like 3 minutes and try to solve it. And now all of you have some answer. Then let's try to now then let's solve this one. So first we have we know the chemical reaction, which is look like this. And now let's apply the rate of the formation and the rate of consumption of the product and the reactant. So first we know that let's first see the rate of consumption of reactants, the NOBr. So we have the d reactants over dt here, and so this is a reactant, so it has a negative sign because its concentration is going down, and its stoichiometry is 2, so we have 1/2 multiplied in front of it. So this is the rate of the consumption of reactant, and actually this whole equation is a rate of this reaction, and this rate of reaction should be the same with the reaction rate calculated from the products. So now we have the rate of formation of NO dNO over dt, so this part, and we need to multiply with the 1/2, which is this 2 is a stoichiometry constant of the products. So this part is rate of formation, and this whole part is the rate of reaction, and they should be the same. I mean that the rate of reaction should be the same that we have got from the rate of consumption of reactant. So now we can have another the expression for the rate of reaction from the product, which is Br2. So since the stoichiometry constant is 1, so we need to have just a dBr2 dt. So actually just you have to confirm, so you have to confirm that the sign on this first, this second and the third term is a positive, because that's the rate of formation of the product, so their concentration is increasing, so we have a positive sign for them. So yeah, so now it's very simple. Now we know the rate of formation of NO, which is the second term. So since we know that, we can easily calculate the rate of formation of Br2, which is the same as the 1/2 and the rate of formation of NO. So we simply plug in this number, then we can easily get the rate of formation of Br2. So now and reversely, we can also estimate the rate of consumption of NOBr by summarizing the first 2 term. That we have the rate of consumption of NOBr is the same as negative the rate of formation of this NO. So now we have the rate of consumption of NOBR is a negative 0.166 millimole, like this. Yeah, so now let's discuss the rate law. So we can define this rate law, which is the speed of reaction in terms of the concentration. It's simply this rate of reaction is the product of some constants with the concentration of reactant or the power of the power of the concentration of reactants. So we can express the equation like this. So it's this K is a constant multiplied by the A over the power of alpha and the B power of beta. So and if the reactant is in the gas phase, we can write it down. We can replace this molar concentration with the pressure. But one thing you have to remember. So here, this power alpha and beta is called the order of the reaction with respect to each species. So this alpha is the order of reaction with respect to the reactant A. The beta is the order of reaction with respect to the reactant B. And then sum of this alpha and beta all is the overall order of these reactions. The one thing you have to keep in mind is that this alpha or beta, which is the reaction order, can be only determined by the experiments, except some special cases such as elementary reactions. And here this case, Kc is the rate constant. So similarly, this rate constant will be determined from the experiment. But we call it a constant, but actually it's dependent on the temperature of the reaction. So more rigorously, it's not actually the constant, but actually within this equation, which is the rate of reaction with respect to the molar concentration, this K is independent of this molar concentration. So although this case, the rate constant is dependent on temperature, since it's not dependent on the molar concentration, we call it a constant. So but just don't worry too much about its dependence on the temperature at this point. And as I say here, for some elementary reaction, we can which occurs in a single step. And this alpha and the beta is the stoichiometric constants of the reaction. So for example, like it says simply A plus B. Not A plus B. So there are some special cases we can just use your stoichiometric constant for the alpha and beta. In many cases, the order of this rate law should be determined from experiment. So, for example, if we consider the reaction between the hydrogen gas and the bromine gas, the rate law for this reaction is not simply just multiplying this rate constant with the molar concentration of the reactants, but it's more complicated form, such as it's not just the function of the concentration of reactant, but also the concentration of product. So just keep in mind that this rate law should be determined from the experiment from experiment, and we will discuss how we determine this alpha. This rate law from experimental observations. So and there is one special case which is called the zeroth order, the rate law. So which is if this order is zero, then this term related to the concentration becomes 1. So this rate is only the function of this rate constant. So if it's a zeroth order rate or zeroth order rate law, then the reaction is independent of the concentration of reactant, but just only dependent on the this rate constant. So the important thing to take away from this this slide is that this rate law, which is the speed of reaction, can be expressed in terms of the the molar concentration of reactant, or the power of the molar concentration with some special power alpha or beta, and this alpha and beta is the order of the reaction, and multiplying and with some the factor of this the rate constant, and more importantly, those like alpha and beta will be determined by the experiment. Then now let's discuss the two special methods for determining this rate law. So first method is the isolation method. So let's consider we have the reaction that reacting two reactant A and B. So then the rate law can be written in this form. We want to find this alpha and the beta value. But if we have a very high initial concentration of this B, much larger than this concentration A, then after the reaction, of course for example, let's say we have the 100 mole of B and the 1 mole of A, and then after all of this A is reacted, then eventually we will have the 0 mole of A, and we will have like a 99 mole of B. So in that case, so after all reactions, the change in concentration of this B is very small. So if this the concentration of B is much larger than that of the A, then we can approximate that the concentration of B is constant to its initial concentration B0. Then since even after a long time since the reaction start, this B is still similar can be approximated to B0. So we can consider this K multiplied by the beta power of this concentration B becomes constant, since this B and the B0 is almost the same. Then we can reduce the this rate law into this form. So this Kc prime include this term, which is the information of the initial concentration of B. So now we reduce this rate law from the two variable into the one variable. So then now by just tracing the concentration of this A, we can estimate we can estimate this alpha or this rate of reactions. So conversely, after we determine this alpha value for which is the which is the power of this molar concentration of A, then we can do the similar thing by just increasing the increasing the initial concentration of A. Then in that case, this A becomes constant. Then we can express this rate law in terms of the concentration of B. Then we can estimate this beta value with respect to Oh, sorry. So yes, so then we can rewrite this rate law in terms of this the concentration of B. Then we can find this beta value from that equation. So now so this is called the pseudo first order rate law. So actually it looks like the form of this equation is a first order, but it's actually exactly the first law because it's we approximate the dependency of this the molar concentration of B. So yes, so the pseudo means it's very close to the real but not actually real. So, and that's because we are ignoring some contribution of this the molar concentration of B. Then let's say we have this equation. Then how do we determine this alpha? Yeah, so in order to determine this alpha value, we use the method called the method of initial rate. So by varying the initial value of this alpha, we can estimate the initial value of the concentration alpha, the concentration A, we can estimate this alpha value. So if we rewrite so this is the equation from here. If we take the log the left and right hand side, then we can express the equation in like this. So log V. So let's say we have the initial the molar concentration of the A0, then the corresponding the rate of reaction is the V0. If you take the log here, we can express it like this. And if we measure this rate for a various initial A concentration, of course this A0 is now much smaller than this the concentration of B. So then we can obtain like those 3 data points, like a V0. Yes, so this is a one the initial concentration 1, 2, 3, and this is the corresponding rate of reaction. And as we discussed in the previous slide, we can estimate this V0 from the time evolution of this concentration, time evolution of the concentration of species A by the like a pressure monitoring or monitoring conductivity or spectrophotometry. So now we have those 3 data points which obtained from those experiments, and let's plot it on this the plot of the plot on the axis, where the y-axis is your log V0 and the x-axis is your log for the initial concentration. Then so this is the first data point, and this is the second data point, and this is the third data point. So this is the special. And then we can draw the line that going through those 3 data points. So if we see this equation, then this the intersect with this y-axis correspond to this log Kc prime. So so the intersect of this line correspond to the rate constant. So we can estimate this rate constant from this intersect, and the slope of this line correspond to this alpha. So by measuring the slope of this line, we can estimate the reaction order of this the species A. So using this isolation method, we can reduce reduce this rate law into the single variable equation, and then by using the method of initial rate, by measuring the the rate of reaction at a various the initial concentration of A, we can and plotting it on the space of the molar concentration and the rate of reaction in a log scale, we can estimate the slope, which is the order of reaction, and the intersect with this y-axis, which can give us information of this this rate constant. Now let's see one example of the method of initial rate. So it is the reaction for recombination of iodine atom in the gas phase in the presence of argon. And now I will show you how we can determine the order of reaction using the method of initial rate. So actually the overall reaction is like this. So two iodine atoms in the gas phase presence with the argon gas, and those two iodine atoms react and form I2 gas. So actually, this gives the numerous the data point for changing the concentration, the initial concentration of iodine and the initial concentration of argon gas. So now this row is the 4 different iodine concentration, and this ABC column is 3 different the concentration of argon gas. So now totally they have conducted 12 experiments. So using this 12 experimental the data point, we can estimate the reaction order and the rate constant. So actually this bottom is the same data point, but we just take the logarithm on the actual data. So then we're gonna use this the logarithm data. So first, let's determine the rate law. So So if you recall the data point, the order of the initial iodine concentration was 10 to the negative 5, while the concentration of argon was 10 to the negative 3. So we can see that the concentration of argon is at least 100 times greater than the iodine concentration. And if you recall the overall reaction, which is this part, you can see that actually the argon is not participating in the overall reaction. So the phase or the concentration of argon before and after the reaction, they don't change. So also if we write down the rate law, the V equals Kr with the argon with the power of beta and the iodine with the power of alpha. Then actually we can approximate them to we can approximate this argon concentration to the initial argon concentration, because this is not a variable anymore. So now we can rewrite it as the Kr, so the effective rate constant multiplied with the iodine concentration with the power of alpha. Then if you take the log, then we have the reaction rate is the log of reaction rate equals the log of effective rate constant plus the alpha log the I. And now we're gonna use the initial rate. We're gonna apply the initial rate data point into this equation, which is this. So yeah, so actually these are the raw data, and this is the data in a log scale. So now we're gonna apply them into this equation. Then if we plot the log V with respect to the log I, then it will look like this. So you can see that there's the x-axis is a log I, which is here, and this y-axis is log v. So this actually this the x is the this -5, -4.7, -4.4, -2.2, and this and this y value is those three. So actually this we have a three different line with respect to the three different concentration of argon. So now we can see that so if we connect the data points for the same concentration of argon, then we can have three lines like this. So this line corresponds to the C, which is the argon concentration equals to -2, and this is B, and this is A. Yeah. So now we can extrapolate these lines. Then we can find the y value where it intersect with the y-axis. So the A intersect at 6.94, B intersect at the 7.64, and C intersects at the 7.93. Then these values then are this log, the effective rate constant, right? So this part is the value when this log I0 becomes 0. Yeah, like here. So this log, the log of the effective rate constant is the y-intercept. And then we have those three values now. And actually, then what's the meaning of the slope of each line? Yeah, the slope is same with the alpha value in this equation. So we can easily calculate this slope by using any two data point in any line. So if we use the like those two line, which is 0.5. Yeah, I think it's AB. So yeah, this point and this point, right? Yeah, so we can use those two data points, which is these two. So the change in log V0 is a change in between those two values, and the change in the x-axis is a change in those two values, which is like this. So then the alpha becomes 2. So then actually we can easily find actually if you pick any two data point within the same concentration of argon, you should get the same answer. And now we know that the order of the reaction for the iodine is 2. So now we need to find the reaction order for the argon. So the way we can find that is using this the data point for the effective rate constant that we have obtained from this graph. So now we have three different the effective rate constants for three different argon concentration. So actually the effective rate constant is a multiplication of the actual rate constant and the initial concentration of argon with the power of beta. So if you take the log here as well, then we got the equation like this. So now we have three data points for like effective rate constant and the initial argon concentration. So if we plot that in the graph, then we have three data points for three different. We have three different the effective rate constant value for the three different argon concentration. So and if we see the y-intercept of this graph, which is we extrapolate this line to the log argon becomes 0, then intersect with the log k effective becomes 9.91. So this value becomes 0. So the 9.91 is the same with this log k rate so the log of the rate constant. Then we have the rate constant of 8.1 multiplied with 10 to the negative 9. And now the last thing we need to find is the slope of this line, which corresponds to the beta value, which is the reaction order of argon. So now we just, yes, it's the same. So we just pick any 2 points and plug into this equation to find the slope of this line. Then we find the reaction order of 1. So now we need to define the unit of the rate constant. So if you see actually from the previous graph we can define the unit of this effective rate constant, which is like this, and this part, the argon concentration with the power of beta, since the beta is 1, the unit is more power than meter minus cube. So then we move to the left hand side, and we have the rate constant unit with the unit like this. And then over the rate law can be written as this, where the rate constant is like this. So now that we know we have the rate constant and order of reaction for each species, where the order of reaction for argon is 1, while the order of reaction for iodine is 2. So as you can see from this process, we can find this rate law from the series of experimental data point varying the initial concentration of reactants. So now let's learn the integrated rate laws. So as we see in the previous, as we discussed in previous slide, this rate law is in form of differential equation. So integrating this rate law can provide us information of how this concentration of reactant or the products changes with time. Yeah, of course, we are able to measure them. The evolution of this concentration with respect to time from the experiment, but we cannot do the experiment for all the concentration for all the time points. So we need to some generate expression for this time evolution of concentration. And from rate law we have derived from the previous slide, we can find the expression for the time evolution of concentration by solving this rate law, which is in a different form of a differential equation. So actually, the concept is quite simple. So since the rate law is in the form of differential equation, so integrating it will give us the solution for the differential equation, which is a time evolution of the concentration of the reactant and the product, which is the rate of reaction. So from now it is more like a math class, but I will go one by one. So just follow my instruction. So let's first start from the zeroth order reaction. So as I said in the from previous slide, in the zeroth order reaction, then the rate law can be written in this form since it's not a function of the concentration of the reactant. So the V is just a Kc. And this the rate of reaction, this V is the negative dA over dt, which is the change in concentration of A over time, and we have a negative sign since A is the reactant. Oh yeah, the reaction we are considering is A becoming a P, and then this rate is the same as the rate of formation of products, so it's a dP over dt. So then, yeah, these two are the same because so this V is also the rate of reaction, and this is also the rate of reaction. So we can rewrite the equation in this way. So dA dt equals negative Kc. So now then we can move this dt over to the right hand side, so we can rewrite as in this form. And if we integrate left and right hand side, and then we are integrating this dA from A0 to A, and this dt from 0 to t. So this is because at time t equals 0, you have the concentration of A0. At a time and at time t, we have the concentration of this of A. So yeah, so integrating dA will just give a will give just A. So it's A minus A0, and similarly in this right hand side, so there is no like a t term here, so we are just having the negative Kc t minus, actually there's a minus 0, but yeah, just ignore that 0 term. So if you rewrite it, so we can rewrite the equation as which is this time evolution of this concentration A with respect to t. Then we can write A equals minus Kt plus A0, which is the initial concentration of A. Then we can see that so if we plot it on in this graph, which is the y is the molar concentration of A divided by this A0, and with respect to time. And since we are dividing it by the A0, it always start from 1, but it just but it decrease linearly, and at some time t, it will all this reactant will react and turn into products. So yeah, so this is so this is a time evolution of the molar concentration A. And as we can see that as we increase this K value, which is an increase, so this Kc is the slope of this line. So as we increase the K value, it will decay faster than the with respect to time. So you can see that as we have a higher K value, this molar concentration decays more faster. So it takes shorter time to consume all the initial reactants. So we can also calculate the time, the half time, which is a t subscript 1 over 2, which is your time to this A becomes the half of the initial concentration. So we can calculate this time, this half time by this relation. So the time to take the A value becomes the half of the initial value. Then the time to get this concentration is the half time, which is a T1 over 2 here. We have the expression for this half time in this form. So this is for the zeroth order reaction. So now let's see the first order reaction. So in the first order reaction, the basic equation is the same, but now we have the different expression for the rate law. So now since it's a first order reaction, the rate of reaction is the product of the rate constant with the concentration of A. So yeah, then now we can rewrite the equation. Yes, since this V this V and this V is the same, so you can rewrite the dA over dt equals negative K now multiplied by the concentration of A. And now we can rewrite the equation as a dA over A equals minus K dt. So now we are integrating the left and right hand side. Yeah, this concentration part from the A0 to A, this time term from 0 to T. Yeah, then if we and this term, this 1 over A becomes log A because your derivative of this log A is the 1 over A. So conversely, so integrating, this 1 over A is a log A. So now we are, now we are integrating from the A0 to A. And this part is the same as the previous slide, so it's just a negative KT. Since there is no T term, so we just have an A, so it's a T minus T0, so we only have the negative KT. If we rewrite the equation, then it's log A minus log A0 equals negative KT. Then we can bring this log A0 inside of this log, then it becomes A over A0 equals KT. Then now we have an exponential form of time evolution of the concentration A. So similarly, we can estimate the half time for this first order reaction. Then we have the half time of the log 2 over K. So here now this molar concentration A decay in an exponential form. And so for example, if we say this is a small k, this is a large k, as we have the larger the rate constant, this smaller concentration decay faster compared to the smaller k value. So the faster decay of this molar concentration of A represents the reaction of the faster consumption of this this reactant A. So the larger the K value means the faster the consumption of this the species A, which is a faster reaction. So so far we have only considered the very simple cases where we have one reactant and one product. But now, how do we deal with if we have the multiple reactants? So let's consider the reaction of A and the B react and the product producing a product P. And here we are assuming the first order reaction for reactant A and the B, which is the alpha and the beta becomes 1, so we can write the rate law as in this form, which is V equals K multiplied by concentration of A and the B. And this since we only have the single, the stoichiometric coefficient is 1 for A and the 1 for B, so you can rewrite it as we can write the rate of reaction as a negative dA over dt equals negative dp over dt. It's the same as a dp over dt. So yeah, since it's a reactant, we have a negative sign here. So it's a product, so we have a positive here, and the stoichiometric coefficients are all 1. So we have no the factor in front of it. Yeah, then yes, so the reaction order with respect to each species is of the first order, but as I said in the previous slide, the reaction order is sum of this the reaction order with respect to A and the B. So the overall reaction is the second order reaction. Then one thing tricky in this expression is now we have two variables, A and the B. So then how we integrate if we have a two variable. So it's very difficult to do that. So the one way is to relate those two variables each other. Yeah, so it's similar to what we did for the monitoring the pressure in the very first slide. So let's say we have the initial concentration of A0 and the B of B0. So and yeah, since it's an initial, so we have a zero product. And let's say we have the X mole of A is reacted, and then at the same time this X mole of B is also reacted. Then we are producing the X mole of P. And so this is the amount that is reacted. Then the remaining the amount of A is A0 minus X. Since this X is amount of reacted, then this value is a concentration of A at a time t. And similarly, we can rewrite the remaining concentration of B at the time t as the B minus X. So here, so I write it as an X, but this X is a function of t because it's the amount of the reacted or the reacted or the produced product after the time t. So yeah, so this X is a function of time. So now we can since this A0 and B0 is a constant, we can reduce here this equation. We can express here the concentration of A and the B only in terms of X. So now we have a single variable. So now let's rewrite down this rate law. Then yeah, so this rate law can be written as a dA over dt equals negative. Yeah, since there's a negative equals a K, and the multiplication of concentration A and the B. But now we can rewrite this the concentration A in terms of X. So it's A0 minus X, and the B is a B0 minus X. So now it's only the function of X. So but yeah, this left term is still the function of A, but we can take the derivative of this this relation. So yes, A can be written in terms of A0 minus X, and if you take the derivative with respect to t, and as I said, this X is a function of t, so it's a dx dt and the dA dt, and this A0 is the initial concentration, which is a constant, so this becomes 0 if we take the derivative with respect to t. So because there is a negative sign in front of this X, the dA over dt is a negative dx dt. Then if we plug in this relation into here, then we can rewrite the rate law in this form, like dx dt equals k A0 minus X B0 minus X. So now it's only a function of X, so we can now it is much easier to solve. Yeah, so then we can rewrite this relation as this form. Yes, multiply both sides with the dt, and the dividing by this A0 minus X B0 minus X. Then we have 1 over A0 minus X and B0 minus X dx equals k dt. And just take the integral of left and right hand side, we can find the solution. And if we see here is 1 over
1 over A multiplied by B, then we can, with a simple mathematical relation, we can rewrite it. We can rewrite the A over A B equals 1 over B minus A multiplied by the 1 over A minus 1 over B. And if you apply it to here, then we can write the inside of integer in this form. And actually, the right-hand side is simply the kt minus the k0. So the right-hand side is a kt. So kt equals the 1 over b0 minus a0 multiplied by the a minus a0 minus x minus 1 over b0 minus x. And since this part is a constant, and we can integrate those two parts separately. So this is so it's integrating 1 over a0 minus x is simply the negative log a0 minus x. And we are integrating from 0 to x. Similar to here is integrating from 0 to x. So we have this negative sign because there is a negative in front of this x. So if we rewrite it, if we plug in this x here and the 0 here, we can rewrite the equation in this form. And since we know from our initial the substitution, this a0 minus x equals a and the b0 minus x is b, so if we plug in this relation into and this denominator, then we can simplify our equation to here. So so here we have the inside of the parenthesis is ln a0 over a minus ln b0 over b, and yet and do some mathematical adjustment, we can have the final expression here. And if we move this denominator to the left hand side, then it's b0 minus a0 kt equals log b over b0 divided by the a over a0. So this is somewhat looks complicated, but just follow this actually follow the one step by one, then we get this expression. And basically we have started from the simple equation of the rate law and the definition of the rate of reaction. And then, like, what if we have the this plus two, the stoichiometry of the reactants is not the same. So for example here, the A plus 2B produce the product P. And if we assume that the A and the B are both the first order, then we can write down the rate law for in a same form with the A plus B cases. However, if we define the rate of reaction, we have some difference here since we have the 1 over 2 here. So from this here, from this starting equation and following the step that I just showed you, you can easily find the relation between the concentration A and B with respect to time. So actually in your the textbook there is the summary of the integrated rate law, and we have just shown that the A plus B cases, which is here. So actually there is a solution for the A plus 2B cases, which is here, and actually showing this resultant equation is the homework problem. So starting from here and following the step that I shown the previous slide, you can easily find this the final relations. And if the reaction is first order with respect to A, but the second order with respect to B, the only thing difference is you have a different expression for the in a rate law. Now you have the power of 2 here. But after that, the procedure is and in this case, even the order of a reaction with respect to B is a second order, the definition of the reaction rate is the same, but only difference is occurs in this the rate law. So initial setting. So there is a difference in this power for the initial setting, but after that, the solving this equation is the same as shown for the A plus B cases.